Welcome back, everybody. This is going to be the final of 3 parts in my lecture series on finding roots of polynomials. In the last 2 videos, we took a look at the rational zero theorem, conjugate pairs, and the fundamental theorem of algebra. In this video, we're going to look at how Descartes' rule of signs can also be a powerful tool for helping us find the kinds of roots and check our work. Let's get started. Now, the good news about Descartes' rule of signs is it applies to all polynomials, not just polynomials with integer coefficients like the rational zero theorem did. So, we can tackle polynomials with more complicated coefficients this way. It tells us something about the number of positive versus negative real zeros. So, the number of positive real zeros is either the same as the number of sign changes, meaning how many times it changes from a positive to a negative coefficient and vice versa, or it's that number minus an even number. We'll take a look at an example in just a minute. I know that's a lot of language. And the number of negative real zeros is the same thing. You perform that same analysis, but you... The number of negative real zeros is very similar. Here, we look at f of negative x and count the number of sign changes. And Descartes' rule of signs tells us that it is either the same as the number of sign changes, or less than that by some positive even integer. By the way, if there is exactly one sign change in the original polynomial, then there is exactly one positive real zero. Or if there's exactly one sign change in f of negative x, then there is exactly one negative real zero. We're going to use all of these rules together in an example. To determine the number of positive and negative real zeros of this polynomial using Descartes' rule of signs. So let's start with the positives, since this one requires slightly less work. We need to find the number of sign changes, in f. Notice I start from positive, and then I change to negative. That's 1. Then I change back to positive, 2. Change back to negative, 3. But then I don't change here. So, there are 3 sign changes. This tells me that f has either 3 or, remember, I can also subtract even numbers from that, right? So it has either 3 or 1 positive real zero. We also know, well, cross that bridge when we get. Now let's look at the negatives. Let's look at f of negative x now. Remember, we need to look at the number of sign changes in f of negative x. In the first term, nothing will change because negative x to the 4th is positive x to the 4th. I will change my sign here. Plus 5x squared. Won't change. Change this guy here. Minus 6. Nothing to change there. So, now, notice that this has only one sign change. I stay positive all the way until the constant term where I change to negative. So there is one sign change. And Descartes' rule of signs tells me that this means there is exactly one real zero. So, how many positives are there? Well, we don't actually know necessarily. What we do know is, we know there are 4 total. There are 4 of them in total. And that's by the fundamental theorem of algebra. because this is a fourth degree polynomial. We know one of them, exactly one of them, not at least one, but exactly one is negative. But there are actually two cases from here that we don't have enough information to determine without doing some further analysis. One case is that there are 3 positive. The other case is that there's 1 positive, and then the other 2 are a conjugate pair. Remember, Descartes' rule of signs only tells us info about real zeros, not necessarily complex ones. In this video, we learned how to use Descartes' rule of signs to analyze polynomials with real coefficients, not just rational. That's going to wrap it up for this video and for this lecture series. I'll catch y'all in the next one.